Poincare sections and Poincare maps. Now what we are going to do here is quite a bit different from the sort of thing we have been doing so far. So let us think of a system like this. Q dot is equal to f of q t. There is no epsilon here, it is not small. F of q t plus capital T is equal to f of q t for all q t and some capital T greater than 0. So this is a periodically forced system, or otherwise non-autonomous. Okay. One way to think about this system is to think that there is a, let me say, there is a Q1 and a Q2 axis. I am showing only two of them for ease of drawing, and with green I will show the time axis. So this is time. Let us say time starts at 0, and over here we have time capital T. So I can draw another Q1 axis and a Q2 axis here, and I'll ask you to think of this plane here as the Q plane at time t. And this is the Q plane at time t plus capital T. And then over here there is t to t, that's what I mean. Okay, and then over here there is another Q, this is Q1, this is Q2, and this here is Q2. Now you think of some initial condition in this Q plane, and as time evolves, Q1 and Q2 change, and eventually we reach this plane. Okay, so this initial condition ends up here, and then there is another plane here, and this same initial condition evolving again from here ends up here. Okay, so this plane here, this plane is called a Poincare section, as in section as in the same sense as cross section. It is a plane here. Okay, this red one here is a trajectory. This point here is where it cuts the Poincare section. From here, from this plane to this plane, we go forward by integrating what? Integrating this governing equation. Okay, so now let me say that this point here is Q, and I will put a bracket here to indicate 1, that, or 0, let me make it 0, so that is the initial condition. And then the differential equation governs the evolution along this trajectory, and I end up with some other point which I will call Q1, and then the differential equation governs the evolution until I reach some other point which I will call Q2. Okay, so Qk gets mapped to Qk plus 1. Since it is a map from a point on the Poincare section to a point on the Poincare section, This is called a Poincare map. Why am I saying that these two sections are identical or equivalent? That is because the dynamics is time periodic. So what happens is the rules that govern this initial condition moving to that, they are the same. So let me explain. Suppose I take this initial condition and it evolves and comes here to this triangle, and then this triangle evolves and comes here to this square. Now if I were to take this same triangle, well, maybe here, then if I let it evolve, it will come to the same location as the square. This is because the evolution from here to here is the same as the evolution from here to here. Okay, this idea has already been used in Floquet theory for linear systems, but here we are thinking about it in nonlinear systems, and we are thinking of this as a mapping, and this mapping does not depend on k because this is time periodic. Now when we think about it as a map, when we think of qk being mapped to qk plus 1, in this way we get a sequence of points qk. So that's one thing. The other is that ODE solution is implicit. It is in the background. If we can solve it analytically, we do it. Otherwise, we use ODE 45 or some other tool. It doesn't matter. It's irrelevant. We will just assume that we know how to integrate ordinary differential equations accurately. Okay, so then we look at the properties of the map. Now, a dimension reduction has occurred, right? So over here, suppose this circle were to get mapped to the same point, then again it would get mapped to the same point. That means this is a periodic solution. But for the map, it is a fixed point. Okay, so over here, if I think of this as qk plus 1 is equal to some function of qk, then a periodic solution of this equation, a periodic solution of this equation represents or represented by a fixed point of f. So q star, f of q star is equal to q star. Okay, this fixed point itself may be stable or unstable. So then we may be able to say things like q is, well, qk is equal to q star plus xi k, let me write it, xi k. Then I will have qk plus 1 is equal to q star plus xi k plus 1 is equal to f of q star plus xi k is equal to f of q star plus df, and you are familiar with this from Newton's method, df q star xi k plus order xi k square. which we will neglect, and we will then have a linearized stability analysis. There is also the Poincare mapping. Right? So here what we do is we have our Q1 and our Q2, and we go forward only T. And then here is our plane, that's the Poincare section. Let's call that P for Poincare section. We take an initial condition here and it maps forward to this point. And we just push it back over there, and then we map it forward again. And then we push it back over there, and then we map it forward again, and so on. In this way, we think of F is a map from P to P. Okay, and this map is called a Poincare map. Looking at the Poincare map can actually give us a great deal of understanding of some systems where otherwise solutions just look arbitrary. Okay, so let me show you some of that with MATLAB now. So here we are in MATLAB, and I have my error tolerance set up, and this you may recognize is the Duffing oscillator. You see y1 dot is y2, y2 dot is like this. This is a Duffing oscillator with a negative linear stiffness. So let me write that down here. So we are now looking at the Duffing oscillator. Duffing oscillator is just an oscillator with a cubic nonlinearity, a linear term, a cubic term, a damping term, and a harmonic forcing term. So we are looking at this one now, x double dot minus x plus x cube plus cx dot is equal to f sine omega t. So there is damping, there is periodic forcing, and over here, if you look at it, if you linearize just the oscillator part, you see that it is unstable. Okay, so there are actually three equilibria. Equilibrium requires x to be 0. If there is no forcing, then there are three equilibria. One is 0, one is plus 1, one is minus 1. And in fact, if you think of this as a spring restoring force, then it is this would be stable, but this is like that. So this is an equilibrium and it is unstable. This is an equilibrium, it's stable. This is another equilibrium, this is stable. So that's the unforced, undamped part of this Duffing oscillator. And then after that we add damping and we add forcing. C, F and omega are free parameters in this system. And now when I go to MATLAB, you will see I have chosen this for an example. F as 1.6, omega is 1.4, C as 0.1. Don't make the mistake of thinking that omega equals 1 is a resonant frequency here, because around the central point, the symmetrical point, that is unstable. It doesn't even have a natural frequency. There are no oscillations there. But here is our system, and what I will do is I will plot it with some arbitrary initial condition. This could be different sometime, and then when I plot it, solve it and then I plot it, this is what the solution looks like. And you can see that after some initial transient period here, then it has settled down to a periodic solution. Okay, it does not look like a sine, it looks more like a straight line somehow over here, not exactly but approximately straight. So it's not a pure sine, it has harmonic distortion, but there is a steady state periodic solution. Let me try this. Let me try a different initial condition. So there is damping anyway, and then with this slightly different initial condition, there is a different transient, but the steady state solution is pretty much the same. Okay, so this is a strongly nonlinear system. We looked at the Poincare section. I'm sorry, we haven't looked at the Poincare section yet. We will look at it soon. But here are other parameter values, and these are more interesting. They show a type of solution that we have not seen so far, and here it is. So you see that it has this peculiar solution. It does not look periodic. It seems like it is on the negative side quite often and on the positive side not very often. But if we run it for longer, then we may realize that that is just an impression. There are many parameter values for which it will show such behavior, but this is just one of them. Okay, so now here we are. Let me zoom in, and you will see that it has these sort of very irregular looking behavior over here. Let me zoom into this part. Let me zoom into this part here, and you will see that it has a lot of time on the negative side and not so much on the positive side. But if I zoom in here, then you will see that it has a lot of time on the positive side and not on the negative side, and it is clear this is not a periodic solution. Okay, so it is an aperiodic solution. In fact, it is a chaotic solution. Okay, so we want to understand this a bit, and here's something that I will do. What I will do now is I will make the integration more accurate. I will make it as accurate as I can, and then what I will do is I will integrate. So now omega is 0.4, so the time period is 2 pi over 0.4. So let me say 100 times pi by 0.4. That is an integer number of periods of forcing. So let me do that and see how well we do on that. This will take a little longer because we are trying to get a very accurate solution. And now you see, because I have gone for an integer number of forcing periods, I can assume that transients are dead. Here they are. So, after some transient period, we can hope that transients are dead. This is what the general behavior of this system is going to be like. I can take a longer time period and throw it away, but we will just take this one. So we will say x0 is equal to x at the end. Okay. So now that is an initial condition that is exactly on the on whatever steady state behavior there is. Okay. So here is what I will do now. I will take this same initial condition and I will integrate, only not for so long. Let me do 40. And let me take another solution where I solve it with an initial condition which is (10 to the power minus 14 times some random). So very, very small difference in the initial condition. Okay, so let me solve that one. So one was x and one was x1. Oh, I made a mistake. I'm sorry, I made a mistake. Okay, doesn't matter. I'll just do it again. I will say t1 equals t. I have to save that because even the t values will be different. So I have to just run that again. Okay, I hope you understand what I'm doing. So there is a t1 and an x1 which corresponds to a solution which is very slightly different, and there is a t and an x. Now if I plot tx first component and t1 x1 first component. I want to see how they behave. So it seems like they are just really following each other. Yes? Is there a difference between them? There should be a difference. How much is the difference? The difference is in the 5th decimal place. Okay? So the difference started in the 14th decimal place, but it has come to the 5th decimal place, and that just tells me I should run it a bit longer, maybe 70. Okay, so here. $76. Okay, all right. You will see why I am doing this very soon. It's just a demonstration. It sort of is to me very interesting. Okay, so here please notice same initial condition x0, tx 76 periods, 38 periods, and over here t1 x1 very slightly perturbed initial condition 38 periods. Okay, and now if I plot, then something very interesting has happened. You see that it seemed like the two trajectories were together for a very long time, but eventually they diverged, and now they are quite far from each other. So if you look here, you see this has become quite far now. Like if you look at this part, it is quite far from here. The difference between this and this in the solution is same order as the solution itself. The difference is almost 3. Okay, so you can see that there is a very large difference now, and if we want to understand this difference, a good way to do it is to do the following. Let me insist on getting the same solution at same instants of time. That is important. This is a mistake that you should not make, because otherwise it will choose slightly different instants of time and you will not be able to see anything. So now I will get the solution x and the solution x1 at the same instants of time, and that's important. That's important because then we can subtract one solution from the other and look at the evolution of that. So now what I will do is I will do semi-log, and then I will do t, because t is t1, right? So if you look at norm of t minus t1, it should be 0. T is t1. So I will look at semi-log y t, and then I will look at abs x1 minus x1 1. So this is the difference in the two solutions. Okay, so I'll look at it on a log-log plot, and this is a most marvelous thing, because you will see that we have started at 10 to the power minus 12. Minus 13 was the original difference between them, and 10 to the power minus 12 was the integration accuracy. And then at some point what happened is the difference between them was actually within the control of the integration algorithm. So below that it is noise, but now over here the integration, we can think of it as accurate, and you can see that there is on average a linear growth on a log scale, which means on average there is an exponential separation between nearby trajectories until the separation becomes comparable to the size of the solution itself. Okay, so over here now these are basically independent solutions. So these started very close to each other, but the separation continued. This exponential divergence of nearby trajectories is not uncommon in linear systems where you have x dot is equal to x, for example. So if you separate two things by a small amount, 0.01, then the separation will eventually become 0.01 times e to the power t, and so exponentially it will diverge and diverge and diverge. But over here, this is a nonlinear system. The separation between the two saturates at some value on average. See, on average, this is still an oscillating quantity. You can look at the separation itself as follows. You can look at it as follows, plot. And it will seem like it suddenly appeared, right? So it will seem like it was 0 for a long time, and then suddenly it is just, they are widely separated. These two have actually almost nothing to do with each other, except that they have the same statistical properties. Okay, so now what does this look like on the Poincare map? So on the Poincare section, what we can do is, we have defined the Poincare map or the Poincare section. Over here, all the points that we get, right? So if we run this for a long time, then we will get a bunch of points on this plane, right? Q1 versus Q2, and we can just plot those and look at those points. Okay, so that's what I want to do now. This is something that takes a bit of time to do very accurately, and what I will do is I will loosen the tolerance a bit, but you can repeat it with a tighter tolerance and you will see that you get essentially very similar results. Okay, and then what I will do here is I will start with x0, there is no problem. Over here, this will be linspace 0, let us say 100 times 100 is too small, but that's all we have time for over here. You can do it for a longer time frame as a part of an assignment. So over here 100, that is 50 periods. Let me do 200. So that is 100 periods, and I want the first point and the last point, so there should be 101 points. Okay, so these are what I will get are 101 points on the Poincare map. Okay, all right, let's see how long that takes. That didn't take very long. So if that doesn't take that long, we can do maybe 1,000 points. So we'll get 500 and 1. It's taking a second, but it will be done. There it is. And then what I will do is I will plot x1 and x2, and I will plot dots. You should do this with 5,000 points or 10,000 points and you will get something very interesting. But let me just give you the initial thing. You can see that there is a very complex layered structure here, right? So you see there is this loop here, and you see there is a loop here, and if you zoom in, then you will see that there are loops inside that, right? And what we can do now is we can do hold on, and we can say x0 is equal to, the end point. So that's whatever it is at the end, and then we can just do 1,000 more. Give me a second or two. Please be patient and think about that plot there, and we will add these points as well. I can plot these with red, and then you can see that the red and the blue are perfectly mixed, right? The statistical properties of these points are really the same, and you can see there are lines here, there are lines here that they are following. It turns around here, and let me make this 2,000 and 1,001, and we will wrap up after this lecture. But you can see that there is a fairly complicated structure over here. This set of points, if we run it for an for an extremely long time, then it will be a set of points with very fine structure. That structure is called a fractal structure. By some very interesting methods of counting the dimension of the set, it seems like the set has a fractional dimension, so that is a fractal set. Moreover, it is an attracting set, so it is a chaotic attractor. It is a different type of solution than we are used to so far in this course. Let me make this one with magenta, and you will see that we are slowly filling in, right? So we have more detail. Now it seems like there is more magenta because there are twice as many points, but you see blue and other things are actually there. Okay, so when we come here, that set of points many points, right, are a subset, right? Because actually there is an infinitely large number of points here now. If there was a periodic orbit, it would just be one point. But over here it seems like there is a very complicated structure. It is the sort of structure that you get from something like this. You take something like this, then you stretch it, then you fold it, then you stretch it, and then you fold it. Please forgive my bad drawing. I cheated a little over there. And you stretch it and you fold it and you stretch it and you fold it, and it gets this very finely layered structure. Okay, so that is the sort of structure you are getting over here. Let me plot this with green. So now we have quite a few points, but actually if you want to look at it in detail, you will need still more points. But if you look here, you will see that there is a loop there, there is a loop here, there is a loop here. In this loop also, you will see that there are actually several loops. If you take many points, you will see that. If you look at this thing which looks like a line, when you get close, you will see that there are several lines there. Over here, what looks like a line will open up. Over here, what looks like a line, you will see that there are many. And this thing which looks like a line, if you take thousands and thousands of points, then you will see that there are actually many lines there. So these things are called self-similar structures. Okay, so these sets are self-similar. There are very simple fractal sets that people draw. There are see, you can take, this is the Cantor set. You can start here, remove the middle third, so you will have this. Then you can remove the middle thirds, and then you'll have this. And then you can remove the middle thirds, and then you'll have this. And you can continue this to infinity, to as many, to infinitely many times, and then you will have a very large number of intervals of very small length. The total length will be going to 0, right? Because over here it became 2/3 of what it was, and then over here it became 2/3 of what it was. So if you take total length, then it goes to 0. Yet there are too many points. It is not one point. It is not even a countable infinity of points like rational numbers. Okay, so this has a fractal dimension. This is a fractal set. This particular one is called the Cantor set. Okay, it has a fractal dimension fractal, think of it as fractional dimension. And these are things that we will see later, but you can read this part for your own interest, and maybe in a discussion session you can tell me about what you have read. Let's go back here. We will stop with this simulation here and what I want to show you in a later lecture is what happens when we look a little more closely at these kinds of maps, at these kinds of fractal behavior, at these chaotic solutions, at the exponential divergence of nearby trajectories. Although the trajectories remain bounded, we will try to understand the nature of this attracting set that we have now discovered, and so on. So all of this falls into the subject of chaotic dynamics, which, as I had told you, I will not emphasize too much in this course, but we will cover some of the more important ideas. Thank you.